In this video, I'm going to talk about intuition behind differential equations and circuits. A lot of people probably have taken a differential equations class, and it's easy to lose sight of the connection between that and circuits when you just learn about it freshman year and you're not really applying it. So let's say you're given this differential equation here, where you have y plus some of its derivative equals some other signal. And usually how this is relevant to circuits is you think of x of t as the input, y of t as the output. And so what we can kind of gather just from first glance is that given some time t, we know that the slope depends on the difference between the input and the output. So if we just rearrange this to this, we see that the derivative of y equals some sort of scaled difference between the input and output. And for simplicity here, let's just imagine these constants of tau and c are equal to 1. And if the difference is 0, output's not moving. If the difference is large, the output's moving pretty fast. So let's take this example here, where we have before t equals 0, both x and y are equal to 0. So there's no difference, the derivative is 0, the output, or y, is not moving. And let's say that we want to set x of t equal to 7, so it's a step input. X of t goes from 0 before 0, rises all the way up to 7, and continues on from t positive. So at first approximation here, if we have a difference of 7 between the output and the input, since we're setting these equal to 1, that means the derivative should be 7, a slope of 7. So let's just see here, after about a half a second, we should be about here. This is 3.5 up after half a second for a slope of 7. Now here, if the difference between the output and input is 3.5, then our slope should be 3.5. So kind of, let's see, 1, 2, 3.5 for here. We'd go up here. Now our difference is, let's just say it's 2. Our slope would be 2. So if this is 1, we'd want to raise up here and 1. Yeah, so you can see as we're getting closer and closer, our slope decreases because our error is decreasing at any given instance of time. So just to kind of connect the dots even more, this should seem pretty familiar, this kind of response. And in fact, we're going to see that this is as if you have a typical RC circuit where the output, y of t here, and the input, the step, is x of t. And this is our c. And in fact, yeah, we're going to prove this. And if the output didn't depend on its derivative, so this term is just 0, then we have some output relevant to some input scaled linearly. And that would mean that as x goes up to 7, y is just some scaled version of 7 instantly. So if these are 1, y is going to mimic that perfectly. No delay, and that's just a resistive divider. You can think of it like that, where voltage division is such that this relationship holds. So that's cool, but how do we find the output relation in time exactly from the differential equation? We know that it kind of slopes up and, single pole if you look at my last videos, but to be particularly mathy, we can just do the Laplace transform and notice the inverse Laplace to get the time domain representation. So some background, we know that we have some input signal, we have a system, and some output signal. What we can think of that as, we have some input signal, which is the step. We have the system, which alters that signal somehow to give us our output. And in the Laplace domain, some background, derivative differentiation is just represented as multiplying by s. Integration is represented by multiplying by 1 over s. And the Laplace transform of a step is just 1 over s. So if we're given this equation here, which is our original equation, to convert it to Laplace domain, we have a differentiation, so multiplied by s. Time domain to Laplace domain goes from t to s. Here, it's just a linear factor of tau, so that stays. Again, t to s. Here, t to s, linear factor of c. And if we just rearrange our terms here, we have y of s times this quantity equals x of s over c. And so what we really want is y of s so that we can take the inverse Laplace and then get the time domain representation. So we know x of s is 1 over s here, if we look at this equation. But now we don't know what h of s is, so we can't really find y of s. What we can do, the more complicated method, I think, is, it's a single pole response because we have one energy storage element, the capacitor. That also because there's only a single derivative, so single pole response first order. That the first order response has to look something like this, where either B or C could be zero, not both of them at once, or they could both be finite. And you take the initial value theorem and the final value theorem, but that's pretty complicated. So what I'm going to do is first find h of s when x of s equals 1. And that is the impulse response when x of t is an impulse, or just a very brief pulse. That should be a pulse. Then the Laplace transformation of that is just 1. And it's pretty powerful because this result says that all LTI systems are characterized by their impulse response. So I'm just kind of brushing over that, but that's a pretty powerful statement. And here's our equation, original again. Now we're going to set our input to just this impulse, and we're going to observe what the output does. So intuitively, we think that if there's impulse in, we're going to have some instant output seen, and then it'll decrease as the capacitor discharges. And we can also think of that in terms of difference between input and output and how the derivative reacts just as before. But if we look at x of s equal to 1, we know that h of s equals y of s over x of s. X of s is just 1, so the transfer function is the output relationship. And we can just solve for that, and we get either this form here, 1 over c times 1 over s plus 1 over tau. Or if you're looking to plot the Bode plot, I like it in this form here, because then when s is greater than 1 over t, then we start to decrease by 20 dBs per decade. And again, this is a familiar single pole roll-off for the simple RC. But if you're trying to do the inverse Laplace, I think this form's easier because from the table that time domain of e to the minus scalar times t looks like 1 over s plus a, where a is the scalar 1 over tau in this case. So now we know that the impulse response is some constant times a decaying exponential for t is greater than 0. And that's exactly what we expected from the start here. So that was a pretty big tangent, but now we know what h of s is. It's just this here. And now we know our x of s original is the 1 over s for the step response. And we can find the output as the impulse, or as the transfer function times the input. And if we do that, we see we have this guy here, and we have our 1 over c, our first order pole, and then our step response. And to find the inverse Laplace of that, we could do partial fraction expansion, find some new coefficient over s plus another coefficient over s plus 1 over tau. Or if you have a fancier table, the table will actually have this entry here, which says that if you have a form of these two factors, because this is pretty common, then you can extrapolate it to be this. And so what we have is this, and if directly relating these two guys here, we can see that this is obviously tau over c times 1 minus e to the minus t over tau as our time domain. And this is exactly what we wanted to look at because that was what we expected from this with our just estimation of how the time response would look. So that's pretty cool. And some extra info, if this ratio of tau over c is just 1, which is the gain, that means that after t equals 1 time constant, so after 1 time constant has elapsed, our output is at about 63% or 0.63. And then after 4 time constants, that's usually the settling time. We're at within 2% of our final value. And then a last little tidbit, it takes 2.2 time constants to go from 10% here to 90%. And that's called the rise time.